All right, let's dive into a really fascinating puzzle that's popping up right at the heart of AI. It's something called the scaling paradox, and it's all about why bigger isn't always better. So here's the big question, the one that's kind of messing with everyone's heads. We're building these absolutely massive, incredibly powerful AI systems. So why does it feel like we're getting less and less bang for our buck? It just doesn't make sense, right? And believe me, this is a problem that's catching even the experts off guard. Okay, so this brings us to what we're calling the scaling paradox. And really, it's a tale of two totally different kinds of limitations. So check out this graph. For years and years, AI progress was all happening down there in that blue zone, what's called the compute limitation area. The formula was super simple. You wanted better AI, you just threw more computing power at it, easy. But we're not there anymore. We're now creeping into this gray zone, the interconnect limitation zone, and this is where things get tricky, because suddenly the problem isn't the computers themselves, it's the connections between them. And man, that's where the costs just start to go through the roof. And yeah, that old strategy was just so straightforward. The whole industry was basically built on this one simple idea. More raw horsepower equals better AI. All you had to do was build bigger and bigger clusters of processors. Simple as that. But the game has totally changed. The old way of thinking that compute power was the only bottleneck, well, the new reality is it's the connections. It's the network linking everything together. We used to think, that costs would scale pretty predictably with performance, but now costs are actually growing faster than the performance we're getting out of these systems. It's like the rulebook for building powerful AI has been completely thrown out.
So what in the world is causing this? It's time to uncover the hidden culprit here.
Okay, the villain of our story has a name: interconnect instability. Now, the official definition is a mouthful. It's an emergent structural property of large-scale systems where the network becomes the primary source of performance degradation. Phew, okay, what does that actually mean? It means it's not about one single part breaking. It's about the entire system becoming unpredictable and fragile because of how all the pieces are connected. A really good way to think about it is this. Stop thinking about a single broken part. Instead, picture a massive citywide traffic jam, on one of those crazy, complex highway systems. One little fender bender, one small slowdown in one spot can cause total gridlock for miles and miles, even if every single car on the road is in perfect working order. That's what we're talking about. And get this, instability isn't just one problem. It's like a whole family of really sneaky issues. First, you've got silent degradation. That's where your performance just kind of slowly drains away with no big warning lights or errors. Then there's something called straggler cascades, which is basically a domino effect. One slow part holds up the next, which holds up the next. You can even get these weird energy feedback loops where the power being used actually starts to make the system unstable. The point is, these aren't big, obvious crashes. They're these subtle, creeping failures that are almost impossible to track down. Okay, so this leads to a pretty big question, right? If all this is happening, why the heck can't we see it? Well, that brings us to why our tools are totally blind to this problem. So for decades, whenever we wanted to know if a system was healthy, we looked at all the usual suspects, right? Things like latency, bandwidth, CPU and GPU usage, error rates, all that stuff. And look, these things are still super important for checking if an individual piece of hardware is doing its job. But, and this is the huge but, here's the problem. All those metrics, they only measure individual parts in isolation. They're great for telling you if one server is okay or one network switch is working. What they can't tell you is how they're all playing together as a team. This slide is really the aha moment. On the left, you see how our old tools view the world as this neat, simple stack. You've got compute, network, storage, all in their own little boxes. But the reality is the messy, complex web you see on the right. That's the operator graph view. And in this view, you can see that everything is connected. A tiny problem in one little corner doesn't just stay there. It spreads, it propagates through all these connections, creating these massive slowdowns that our old tools, looking at their neat little boxes, are completely blind to. So what's the bottom line here? What does this actually cost? Let's talk about the real economic damage from all this instability. And believe me, the damage is very, very real. We're talking about those soul-crushing, endless job reruns that waste tons of time and energy. We're talking about a massive drop in how much of your super expensive computer cluster you can actually use. We're talking about blown deadlines and broken promises. And maybe the worst part? You've got these brilliant, expensive engineers spending their days hunting for ghosts in the machine instead of building cool new stuff. This timeline here shows you exactly where the money goes down the drain. See all that blue? That's when the system is actually doing useful work, computing. But look at all that gray. That's communication and synchronization. That's the system just talking to itself, trying to get organized. And all that time, the meter is running, the electricity bill is climbing, but zero useful work is getting done. That's the instability right there, turning directly into wasted cash. And you know what the first instinct is, right? Just buy more hardware, throw more servers at it. But that's a trap. It doesn't work. In fact, over-provisioning usually makes the problem even worse, because you're just adding more complexity and more potential failure points into that already messy web. So what's the answer then? Well, it's not about better parts. It's about a whole new way of seeing the problem. We have to shift our focus away from the individual components and start looking at the bigger picture, the structure of the system itself. And this quote from the source material really just nails it. It says, "Interconnect stability must be understood as a structural property rather than as an operational anomaly." Let that sink in. What it's saying is, this isn't a bug you can just fix and patch. It's a fundamental part of the system's design. It's built in. So this means we need a totally new approach. First, we've got to stop staring at individual parts and start analyzing how the whole system interacts. Second, we have to start treating stability as a core economic issue, not just some techie afterthought. And third, we desperately need new tools that can actually see and analyze that operator graph so we can finally understand how these problems spread and, actually do something about them. Which really leaves us with a huge question for the future of AI. As these systems get bigger and bigger, who's going to win? Is it going to be the companies that build the absolute fastest, most powerful chips? Or is it going to be the ones who finally figure out how to master the complex, invisible connections that tie them all together?